We have now completed several modeling problems where the input was a force. And in this presentation, we're going to look at an alternative input to the spring mass problems. Here the input will be the displacement of one end of a spring. So here's a simple example. We have a mass on a spring, and one end of the spring is connected to a plate, and that plate has a specified displacement, which is x, and this is the input to the problem. The output is the displacement of the mass away from its equilibrium position. That's specified as y. We've seen a few applications with this kind of input. One that comes immediately to mind is that of the quarter car model. In the car problem, the car is moving across an uneven road, and as it moves, the tire will move up and down with the road surface. This displacement is then transmitted to the car through the suspension stiffness. Now let's write our equations of motion for this scenario. We'll start with our free body diagram. So here is the mass. Its displacement in the up direction is labeled y. The force from the spring, Fs, is shown acting upon the mass in the upward direction. That's the positive direction for this variable. And then we can write the equation of motion, my double dot equals Fs. Now we need to figure out the relationship between Fs and x and y. To do this, we'll do the following thought experiment. We'll hold x equals 0, and then we'll increase y. And we'll see that in this case the spring elongates. So when the spring elongates, we know that it will be pulling downward on the mass. So the spring force must be equal to Fs equals minus k times the elongation. Since when elongation is positive, we know the spring force should be negative. Now, elongation of the spring will be y minus x, and therefore the relationship is Fs equals minus k times y minus x. That gives us the following equation of motion, my double dot equals minus k times y minus x. We'll just do a little algebra to move all the y terms over to the left-hand side, and then we have my double dot plus k times y equals k times x. Now we'll find the transfer function. We'll take the Laplace transform and set all the initial conditions equal to 0. And that yields the term ms squared plus k times y of s equals k times x of s. We divide both sides through by ms squared plus k, and that yields the relationship y of s equals k over ms squared plus k times x of s. We'll then divide the numerator and denominator by m, and we'll introduce the notation omega n equals square root of k over m. After a little bit of algebra, we'll find the relationship y of s is equal to omega n squared over s squared plus omega n squared times x of s. So you can see the transfer function here between the input displacement x of s and the output displacement y of s. Omega n is, of course, the natural frequency of the mass m on the spring k. Here we see an experiment with an input displacement. The input displacement is in the base plate, which we label x, and then the mass on the end of the cantilever beams, displacement there is y. And our simple mechanical model of this system is as shown in the box